All right, so it is 3:30. We can go ahead and get started. Yeah, how's everyone doing? You excited about spring break? No, I am. Cool. Yeah, me too. Yeah, hopefully you guys are able to find yeah, at least a couple days of, nice relaxation. Yeah, away from class, away from homework assignments. But yeah, so we do have our final homework assignment due this Friday. I will be posting another homework assignment on Friday, but yeah, it'll basically be due, not the Friday of spring break, but the Friday after that. So if you have any questions, you can feel free to post on Piazza. However, the response time on Piazza might be not as quick as it typically is, during the regular, days of the semester. So just kind of keep that in mind. But I will have office hours this week. I'll have, office hours next week. So if you have any questions, feel free to let me know. Right. And so what we're going to do today is we're going to just quickly wrap up with the DB-scan clustering algorithm, talking about just some of the just general benefits and drawbacks of using this algorithm. And then we're going to move on to Unit 9, in which we are going to be talking about fuzzy C-means clustering. And so like we discussed, fuzzy C-means is basically the fuzzy clustering extension of the K-means clustering algorithm. So we're going to see a lot of similarities in how these two algorithms work. So yeah, so any questions before we get started? Okay, cool. So very quickly, one of the cool benefits that we were talking about that DB-scan has on Tuesday is that, in addition to being the first clustering algorithm that we've talked about that can help us simultaneously identify clusters and noise, it can also, given the way that it's designed, help us identify clusters of any shape. However, we do need to be careful in order for the clustering or in order for the DB-scan algorithm to work effectively. We do need to make sure that our clusters are well separated enough and they do have roughly similar sparsities. Otherwise, we might run into a situation like this in which we basically have like a core point bridge that that unfortunately ends up linking these two close clusters together. And like we discussed, like something that we could try as well, we could simply try making our epsilon value smaller such that this bridge is not crossed in core points. But the downside of that is we have this more sparse cluster. So if we make our epsilon value too small, we do end up getting these more sparse clusters that never really fully join all together. So something to think about. Yeah, so I think we've discussed all these components here before. Actually, yeah, I didn't realize I actually finished this section, but yeah. Any further questions on the DB-scan clustering algorithm? All right. Cool. Let's move right along to the fuzzy C-means clustering algorithm. Okay. So let's take a look at the data set that we're going to be exploring with our use of the fuzzy C-means clustering algorithm. So just out of curiosity, so the data set that we're going to be exploring in this unit is a sample of observations from the MNIST digits data set. So just out of curiosity, has anybody heard of this data set before, or have you used it before? You're allowed to say no, yes or no. Um, So it's a pretty popular machine learning benchmark data set. So, what we mean by a benchmark data set, we have these very popular data sets that data scientists end up, playing around with when it comes to, exploring how given algorithms might perform on these data sets. So given how popular the data set is, like for instance, if you're creating your own new clustering algorithm, your own new like supervised learning algorithm, for instance, quite often one way to build confidence in how effective your algorithm is to basically apply that algorithm to one of these well-known benchmark data sets, and then you can basically say, well, here's how our algorithm performed on this data set that you all know and love. So one of these common benchmark data sets is the MNIST pixels data set. And there's a couple of different, representations of it. So we're just going to be using a random sample of it. But basically what a row in this data set represents is basically an image of a digit, so 0 through 9, that has been written by, some person, with their hand. And then basically we take a picture of these handwritten digits. And then basically the way that we, translate a given image to a given row in this data frame is we basically take our 0 through, so basically each of these pixels in the image represent a numerical value. So basically 0 is completely black and 255 is completely white. And then we can perform, some sort of normalization of those, pixel numbers essentially. But, what we're looking at here is basically an 8x8 grid of 64 pixel value. So we can simply just take that 8x8 grid and flatten it into a 64 dimensional array of the 64 corresponding pixel values. So what we're going to explore in this class is, what can we learn about the clustering structure of this 64 dimensional data set of each of our digits in the data set. Now, the nice thing is we also have a set of class labels that correspond to each of these images here. So we actually do know the intended digit that each of these images is supposed to be a picture of. Now, if this was a supervised learning class, our overall goal would simply just be, to take our 64 dimensional data set of pixel values and then use it to predict these pre-assigned class labels. Now, given that this is an unsupervised learning class, that is not going to be our goal yet. Now, the cool thing here is that, you can choose to use an unsupervised learning analysis for a variety of different other goals. So one thing that an unsupervised learning analysis can be useful for is to basically explore your data set first before fitting like a supervised learning algorithm to that data set. So if you know that your ultimate goal, for instance, is to eventually successfully predict these class labels, by exploring the nature of the data set first, this can actually give you ideas as to how to make your supervised learning algorithm even better. Now, it may actually not be the case that you plan to use a supervised learning algorithm eventually. It could simply just be the case that you simply just want to learn more about what's going on in these high dimensional data sets. So in this case, an unsupervised learning analysis can also be useful, simply just to learn more about your data set. So in our particular research analysis, we'd like to explore this data set and answer some of the following research questions. So for starters, first I'd like to ask, well, is this 64 dimensional pixel data set, is it clusterable, at all? Is it fruitful to apply a clustering algorithm to this? So we're going to take this 64 dimensional data set, we're going to plug it into a couple of TS&E plots, and we are, in fact, going to see, like we see here, that there is evidence of a clustering structure. And so in addition, if we ever have a set of pre-assigned class labels, a typical follow-up question might be, to what extent do these clusters that we see suggested in our TS&E plot, to what extent do they associate with the digit that the image is a picture of, essentially? So what we're seeing here is there is, this pretty strong association for the most part between each of the actual digit labels that we know with the clustering structure that we're seeing here. So basically, this TS&E plot suggested cluster that we're seeing here has a very strong association with the digit 0. Or in other words, this TS&E plot suggested cluster is very homogeneous with respect to just one class label. And furthermore, the 0 labels, the 0 digits, are completely together in this TS&E plot suggested cluster. On the other hand, we are seeing, some sort of, it's not a complete one-to-one correspondence between the TS&E clusters and the digit labels. So, for instance, we are seeing that like the one digits actually break down into three subclusters. So we might be interested in exploring, is this evidence to suggest maybe that some people are choosing to write the number one like in a variety of different ways. So some people write it like this, some people write it like this, some people write it like this. So this is a situation in which like using a TS&E plot as well as our cluster analysis, other clustering algorithms can, provide useful insight that, maybe if your goal is to, predict whether a given image is a one, this might suggest that you're going to have a little bit, it's going to be a little bit more challenging predicting the one than opposed to like predicting the zero. What this is kind of telling me is that for the most part, there's really only one way to write a zero in this, or at least in this image data set here, but there's different subclusters of one. So we can use these insights here to help us, inform, how we can build our supervised learning algorithm. So maybe rather than predicting just like this vague notion of a one, we can actually make multiple classes of ones that we might be trying to predict. So this one, and this one, for instance. So that's something to think about. And then we might also want to ask ourselves, for the purposes of an eventual supervised learning algorithm, are some of these digits more distinct and recognizable than others? So, for instance, we do see that this zero, based on this TS&E plot, there is some suggestions that it is going to be very distinct. There's not any overlap between these, zero observations and then some other cluster. But for instance, if you take a look at like the 9 and the 3 digits, which are mostly placed in these two TS&E plot clusters, we do see that there are quite a few points that appear to be what we call straddle nodes. Or in other words, they, the 3 and the 9 center, these two clusters here, they're not as well separated because we do have these straddle nodes that exist between them. So, for all of our clustering algorithms that we've discussed so far, they are all what we call, partitional clustering algorithms. Or in other words, if you're looking at a partition-based clustering, each observation is assigned to one and only one cluster. And so ideally, we'd be able to, use a clustering algorithm that can reflect to some extent what we can see here with our eyes. Is that, there are some observations that straddle multiple clusters. So ideally, we'd be able to use a clustering algorithm that's able to reflect that uncertainty of which cluster some of these observations should belong to. So for instance, like an observation like this, ideally we'd like to, we have a strong indication that, this observation, generally speaking, strongly belongs to this cluster here. But we'd like for our clustering algorithm to reflect the uncertainty of the cluster assignment for like observations like this one here. So that's something that we're going to explore with fuzzy C-means. And then we also might want to explore, well, how many of these observations in this data set should we be uncertain about in terms of, what cluster it belongs to? And then, how might we use these insights to better help us design a, for instance, supervised clustering algorithm? So for instance, like, why is it that these particular observations straddle the mostly 3 and mostly 9 clusters? So this can all yield useful insights. So this is going to be our general research goal. But any questions on that? Okay. And so also, this can be useful not just from, a supervised learning analysis perspective, but like if we go back to our country data set that we explored, for instance, so we put this into a TS&E plot and we found that, for the most part, there were about 3 main clusters that were not the most well separated. And so, for instance, one such example of, how you might use clusters of countries is like, the UNFCCC, ends up using country categories to, determine like how much that particular country should contribute towards, mitigating greenhouse gases. But so, for instance, like if you were, a country that existed sort of on the border between two countries, it might not necessarily be the most fair thing to say that this country belongs to this group wholly, or this country belongs to this group wholly. You'd want to be able to reflect the fact that these countries exist sort of at the border to perhaps, give more targeted suggestions about, what strategies they should employ. So basically, using a fuzzy clustering algorithm yields a lot more nuanced insights about the cluster assignment that particular observations should have, essentially. So this can be very useful. So to some extent, we've used some of our clustering evaluation techniques to some extent reflect that a given observation may not be as well assigned to one and only one cluster, right? So for instance, we have a data set such as this, where it's like, we definitely have some straddle nodes, present in the data set and in the clustering that we found. And to some extent, our silhouette plot is able to reflect that. So it does show us, for instance, that there's some observations with low silhouette scores, so indicating that they're somewhat closer than other observations in its cluster to some other cluster. But the nice thing is, and then also, we can also use our cluster sorted similarity matrix as well. And this also kind of, this indicates to us that, for instance, there's some observations like this one here that are actually, quite close to the observations in cluster 2, actually much closer, actually closer than the observations in the cluster that it was actually assigned to. But these are all clustering evaluation metrics, so they're not actually techniques that are explicitly embedded in the design of the algorithm. So none of our clustering algorithms so far have actually embedded this uncertain cluster assignment actually into the algorithm itself. So that's going to be the benefit of our fuzzy clustering algorithms in general. So before we talk about fuzzy c-means, we want to talk a little bit more about just the general way in which a fuzzy clustering algorithm works. So usually your input is, at the very least, your m-dimensional data set with n attributes. And then rather than receiving a partition-based clustering of your data set, instead, what you end up getting is what we call a fuzzy pseudo partition, or also known as a fuzzy clustering membership matrix. Okay. And so a fuzzy clustering membership matrix for a data set with 1,000 objects and a clustering of 4 clusters might look something like this, where every observation and every cluster is assigned a cluster membership score, WIK, where this WIK represents the membership of observation I to cluster K. Okay. Now, in general, we have some additional properties that we usually apply to our to basically our cluster membership scores within this matrix. So number one, we usually stipulate that the sum of the observations or sum of the weights in each row should add to 1. So in other words, each row that corresponds to a observation should represent a probability distribution. Okay. Um, and so because of that, you can also think of this WIK as representing the probability, or perhaps the extent to which the observation xi belongs to the cluster CK. Okay. Now, in addition, we have this additional set of stipulations for our membership score values. So one thing that we stipulate is that if we sum each of the values in a cluster membership score column, the sum of these values should be greater than 0. And so what that means is that every observation, or excuse me, every cluster should not be empty, right? So basically, if the sum of these values was 0, then basically what that means is every one of these cluster 1 membership weights is 0. Or in other words, no observation belongs at all to any degree to cluster 1. So we don't want that to happen. We want every cluster to have at least a little bit of membership of at least one observation in the data set. Otherwise, there's really no point in having that additional cluster, essentially. And then on top of that, we also want each of our cluster membership scores for each cluster. So basically each column in this matrix should be less than m, the number of observations. And basically if that happened, what that would mean is that every single one of these cluster membership score values would be equal to exactly 1. Or in other words, every observation in the data set completely belongs to this particular cluster. And so that would kind of make it, having these other clusters kind of useless, because they would also basically have all zeros. Okay, so we want to use every single one of our clusters to at least some extent. Every observation cannot be assigned to just one cluster completely. So that's what that means. Okay. Now, ideally, this is, if this was our data set here, we'd like for our fuzzy clustering membership matrix to be visualized in such a way. So like this. So for instance, we can color code our data set 4 times. First by the cluster 1 membership scores, or something like this. Next by the cluster 2 membership scores, so something like this. And this is ideally what we would like to see in our cluster membership matrix. We'd like to see, much more of a certain higher assignment value for observations that are further away from other clusters. But we'd like to see much more of a uncertain or a lower cluster assignment for observations that straddle multiple clusters, essentially. So this is more or less what we would like to see. Any questions on that? Okay, so this is the general idea behind a fuzzy clustering algorithm, and there's many fuzzy clustering algorithms that exist. But one of the most common fuzzy clustering algorithms is, like we mentioned, the fuzzy C-means clustering algorithm, which again is, just a fuzzy clustering extension or generalization of K-means. Okay, so the structure is going to be very similar, so let's go through it. So in K-means, like we discussed, our input is a m by n dimensional matrix with n attributes, and we do want to remember this should only be used for numerical data sets. And it's going to be the same thing for fuzzy C-means as well. So this should only be used for numerical data sets. Okay. In addition, so K-means, like all of our prototype-based clustering algorithms, do require for us to stipulate the number of clusters that we'd like for the algorithm to return. So it's going to be the same thing with fuzzy C-means. Okay, now the final parameter that we are going to stipulate in fuzzy C-means is this P parameter. So it's going to be this p value, not the p value, but a value of p that can range between 1 to infinity, so 1 not included. And it's basically going to be a parameter that you can toggle that basically changes exactly how fuzzy your fuzzy clustering membership matrix will be in the end. So we'll discuss this more thoroughly in just a second. But one place that this P or this fuzziness parameter P shows up is when we speak about our overall optimization problem that we are trying to solve in fuzzy C-means. So if we recall, in k-means, our overall optimization problem that we are trying to solve when we, ideally select our k-means clustering is we want to find the k-means clustering that minimizes the squared Euclidean distance from every observation to the centroid of the cluster that it was assigned to. Right. You want to be careful that we're using squared Euclidean distance specifically. Okay. Now this is what we would call a weighted inertia extension. So this is, what we're going to introduce here is simply just an extension of this optimization problem here from k-means. So rather than finding the distance of each point to the cluster that it was assigned to, we're actually going to add up the squared Euclidean distances of each point to each cluster in the data set. Because you want to remember, basically, in theory, every observation to some extent belongs to every cluster in this data set. So we're actually going to want to consider and add up the squared distance of every observation to every cluster centroid in our optimization problem. But then on top of that, we're also, it's not just going to be a weighted, or it's not just going to be the sum of the squared Euclidean distances, but it's actually going to be a weighted sum of each of the squared Euclidean distances from the observations to each of the centroids. Excuse me. And so we'll talk more about this weight in just a second, but this weight, this WIK, is in fact the fuzzy clustering membership score of observation XI to cluster CK. So these membership scores are also going to be used in the optimization problem. So in other words, we're trying to minimize the weighted inertia of our fuzzy clustering matrix W. Okay. All right, so that's the optimization problem that we're trying to solve. However, unfortunately, much like we've seen with our other prototype-based clustering algorithms, it's highly unlikely that an actual computationally efficient algorithm exists, which will find the absolute minimum to this optimization problem. So what we do instead is we use the Lloyd's algorithm heuristic for attempting to find a local minimum to the corresponding optimization problem. So in k-means, we've seen this before, we have our centroid initialization step. It's going to be the same thing for fuzzy c-means. And then much like in k-means, until some sort of stopping criterion has been met, we are going to iterate through the partition calculation step and the centroid calculation step. Now it's going to be the same thing for fuzzy c-means, except now we're going to have the fuzzy pseudo partition or the fuzzy membership matrix calculation step, and then the centroid calculation step. Okay, so there's going to be some slight differences though in each of these steps here. So kind of stay tuned. So the initialization step is slightly different because in k-means, we are randomly initializing the centroids. Now, what's going to be different about fuzzy c-means is that in this case, we're actually randomly initializing not the centroids, but actually our first fuzzy pseudo partition or our first fuzzy clustering membership matrix. So there's some techniques that we can use. So for instance, we'll talk about at the end of the class, the symmetric Dirichlet distribution. It's one such way to essentially, randomly initialize a probability distribution essentially for a given set of observations in a data set. So whichever way you end up, initializing this matrix, you do want to make sure that it does meet these requirements that we stipulated above. Or in other words, the sum of each row should add to 1. So these should be probability distributions. And each of these rows, or excuse me, each of these columns has to be between 0 and the number of observations in the data set. Okay, it's a slight distinction. We're starting off by randomly initializing the fuzzy clustering membership matrix. Okay, now in the centroid calculation step, we are also going to have some slight differences as well, but what we can actually see here is that, this centroid calculation step in fuzzy c-means is actually a generalization of what's going on in k-means. So in k-means, the way that we recalculate our centroids in a given algorithm is we simply just calculate the average of all points in a given cluster, okay? However, you want to remember in fuzzy c-means, all points are assigned to some extent to all clusters. So therefore, rather than taking the mean of a given points assigned to a given cluster, what we're going to do is we're actually going to calculate the weighted mean of all points. And the weight that we're going to be introducing, or that we're going to be using, is the cluster membership of all observations to the particular cluster centroid that we are updating, essentially. And also take note, sorry, what was the color that I was using for that? Also take note that we are using this fuzziness parameter P as well as the exponent for these fuzzy clustering membership weights. Okay. So for instance, if we wanted to calculate the new centroid 1, we would add up the cluster membership weights, raising all of those weights to the P, to cluster 1. So that would be our denominator, and our numerator. We would also use those same weights in each of the points that we're adding up. And so this would give us our centroid 1 point, essentially. Okay. All right. I've been doing a lot of talking. Any questions on that? Okay. Okay. Again, if you have any questions, feel free to let me know, as I'm going through this. All right. And in addition, we also have our partition calculation step in k-means, in which we simply just assigned each observation to its closest centroid. And again, you want to make sure that you're using the squared Euclidean distance to measure closeness. Otherwise, this algorithm will not converge. And so what's different in fuzzy c-means is now we are recalculating our fuzzy clustering membership matrix. And we are, in fact, going to be using, again, the squared Euclidean distances of the observation I to its to the cluster centroid K that we're considering. But we're actually going to be using, so we're not simply just assigning a point to a cluster, we're actually recalculating the cluster membership score for observation I to cluster K. So this is actually going to be an equation that we're setting up here that also is going to use this fuzzy parameter p as well. So we'll discuss, what this equation actually does and how it works in just a second. But this is the equation that we use to update our membership scores for the matrix. So it's slightly different. Okay. However, the stopping criterion for both of these algorithms is going to be the same. So in other words, when your centroids are the same in the previous iteration as they are in the current iteration, that is when you can stop the algorithm. Okay. Questions on that? All right, so let's focus a little bit more on this equation that we use for the fuzzy partition update or calculation step. Okay, so we want to think about, in particular now, what exactly is this fuzziness parameter doing in the algorithm? So in other words, we'd like to explore what kind of results that we might, what kind of results will we end up getting as this p parameter is set to be higher and higher. So let's think about what we might end up seeing here. So let's consider, let's just say we're in a given iteration of the fuzzy C-means clustering algorithm, and we have two current centroid locations, C1 and C2. And so, given that x1 is further away from c1, what that means is that the reciprocal, the squared reciprocal of those two distances will basically have this relationship. Okay. And so we want to focus on what kind of values we might expect in the numerator of this equation, at least to start with. So we can put these two squared reciprocal distances on our x-axis of this, this numerator function here. Okay. And then we want to think about what is going to happen. So for now, let's just assume we were actually simply just looking at, rather than this, 1 over squared distance value here, like let's just assume we were looking at simply just like this equation x, and then x raised to the 1 over p minus 1. So let's think about what happens to, what this function might end up looking like as p goes to infinity. So as p goes to infinity, we want to think about what's going to happen to 1 over p minus 1. So this is like a Calc 1 question. So what's going to happen here as p goes to infinity? 0. Yeah, exactly. So basically, we're plotting this function here in which the exponent is getting smaller and smaller and smaller. So you would expect your function to look something like the square root function, except basically the base, if you will, is going to get flatter and flatter and flatter. So something like this. So the larger that p value gets, the more flat of a function that this is going to look like. Okay. So if we were to actually calculate the numerator value in this WIK equation here, when we're considering basically W, what are we doing here? W11 versus W12, or in other words, the extent to which observation 1 belongs to these two clusters, then we can see that our numerator value for this WIK is going to be relatively comparable. They're going to be approximately equal to each other. And so then what we end up doing in order to force our WIK matrix to have rows that sum to 1 is we end up normalizing by the sum of these row values, essentially. So basically, we're normalizing by the same thing. for W11 and W12. So basically the W11 and the W12 values also end up being approximately equal to each other. So to put it all together, what this shows us is that when we set that fuzziness parameter P to be higher and higher, the types of results that we end up getting in our fuzzy clustering membership matrix is going to look something like this. Or in other words, the numerator of our WIK equation values are going to look relatively similar. And so therefore, the corresponding weights in a given row will look similar. In particular, it's going to be 1 over k, the number of clusters, because basically these rows have to add to 1. So in this case, what we can see here is as we increase that fuzziness parameter P, fuzzy C-means will tend to return very fuzzy clustering membership matrices. Okay. Now let's for a second just assume that we were in fact dealing with a clusterable data set with 6 observations assigned to it. And so the question is a fuzzy clustering membership matrix that looks like this, is this useful? Like pretty much in any clusterable scenario, is this something that we could extract a whole lot of meaning out of? Yeah, not really. Yeah, it's basically saying every observation equally belongs to every cluster. And if we're dealing with any clusterable data set, that's it's not really reflecting the certainty or any degree of certainty about any observations belonging to a particular cluster. So for all intents and purposes, it didn't really actually cluster the data set. So it's not super useful. So therefore, you want to make sure that you don't set that fuzziness parameter to be too high. On the other hand, let's see what happens when we set that fuzziness parameter to be closer and closer to 1. And this is approaching 1 from the right, because we want to remember we can never actually set that fuzziness parameter to be exactly equal to 1. Okay, and so let's just say we have this example here again, in which we're at an iteration of fuzzy C-means in which observation 1 is further away from cluster 1. So therefore, the squared reciprocal of these two distances will have the following relationship. So therefore, again, if we plot those two squared reciprocal distances on this x-axis defined by those values here, then we would want to think about what is going to happen to the numerator of this WIK value for these two squared reciprocal distances here. Or basically, as we raise those squared reciprocal distances to 1 over p minus 1. Okay, so setting up another Calc 1 question for you all. So we want to ask ourselves, what happens to our exponent, 1 over p minus 1, as we approach 1 from the right? So what does this value go to? Infinity. Yep. So this exponent in the WIK numerator goes to infinity. So therefore, what this, if you were simply just doing like x and then x raised to the 1 over p minus 1, you end up getting a function that looked more and more like this. So you have like a flatter bottom and more of a dramatic upturn, if you will, like looking like this. Okay, so that would give me a numerator value for cluster 1 and x1 to be here, and a numerator WIK value for observation 1 and cluster 2 to be here. So in this case, the numerator of my W11 and my W12 values would be dramatically different from each other. So the numerator for W12 would be a lot larger. Okay. So in this scenario, we end up seeing for a given numerator value, for a given observation I, we would have basically one value that is a lot larger than the rest of the WIK numerator values for observation xi. Okay, and then so similarly, for WIK, we normalize by the sum of the numerator values in the, for that corresponding observation I. So basically, if the numerators, or if the numerator has one that's a lot larger than the other, then there will be one WIK value that's a lot larger than the other. And because basically when we normalize, we are forcing our rho to add up to 1, what that will mean is that the weights for a given observation I will have one cluster with a membership score close to 1, and the rest in the row will be close to 0. Okay, so your fuzzy clustering membership matrix will look something like this. So in other words, when you set that value of P to be closer and closer to 1, what that means is, or what C means will tend to do, is it will return what we call a harder assignment. So in other words, a given observation belongs to mostly 1 and only 1 cluster. Okay, now if you got a fuzzy clustering membership matrix that was a very hard assignment, there's not necessarily anything wrong with this per se. I mean, you still are able to extract useful information, right? So you're basically saying observation 100% belongs to cluster 1. Observation 1 100% belongs to cluster 2. But the downside of setting your value of P too low is that basically you could have just run K, like if you wanted a hard assignment in which every observation belonged to 1 and only 1 cluster, then you could have just run k-means and gotten a similar result, which is fine. But the thing here is that fuzzy c-means is actually more computationally complex than k-means. So you kind of just ended up wasting a lot of or more time, if you will, running fuzzy c-means if you simply just wanted a hard assignment. So this result will look like what k-means would return. But you want to remember, k-means is more computationally efficient than fuzzy c-means. You've kind of wasted a little bit of time doing it this way. Okay. Questions on that? All right. So I'm going to do a breakout room. So get ready. So we want to think about, for each of these clustering algorithms, useful evaluation metrics that can tell us a little bit more about the nature of the clustering. So we can see with our eyes here, simply just by looking at this matrix, that this is a very hard assignment. And similarly, we can look at this fuzzy clustering membership matrix here, and we can see that this is a very fuzzy clustering membership matrix. So for instance, we might want to define a evaluation metric, which can quantify the general level of fuzziness that exists in a given fuzzy clustering membership matrix. So the way that or one way that we go about doing that is by using what we call the normalized Duns partitioning coefficient. And this is the equation that we end up using to calculate that. So what we end up doing is we first calculate this WC value. And what this WC value represents is basically what we get when we add up the squared membership score of all observations in the matrix. And then we divide by the number of observations in the data set. And then we use this, so the actual normalized Duns partitioning coefficient is this equation here, where K is the number of clusters. Okay, so question for the breakout room, which I'm about to open up, is what, yeah, so like what, if we were to use that normalized Duns partitioning coefficient, what would that be for this membership matrix? And then if we were to calculate the normalized Duns partitioning coefficient for this matrix, what would that be? Okay, so I'm going to open up the breakout rooms. You can discuss this with your group for the next few minutes, and then we'll meet back and discuss. So let me set this up. Okay. I'm going to set up 3. Okay. All right. You can choose your own breakout rooms. In the interest of time, I'm just going to start randomly assigning, but you can always change them. All right, so welcome back. All right, so for this fuzzy membership matrix, what did we end up getting for the normalized Duns partitioning coefficient?
The answer would just be one.
Yeah, exactly. So generally speaking, we will end up seeing this relationship for the fuzziest of any possible fuzzy clustering membership matrix that we could create. So for, if we have a completely fuzzy clustering membership matrix such as this, what we would end up getting for this WC value is simply just a value in which we are so basically, every single one of these cluster membership weights would be 1 over k, the number of clusters. And so what that means is we're simply just adding up k times m 1 over k squared values. And so when we simplify that, we get a WC value of 1 over k. And so therefore, when we plug in that WC value here, we get 1 over k minus 1 over k in the numerator. So we get, oh, sorry. Yeah, so this should actually be a 0 here. Okay. Any questions on that? All right, so this is how we would interpret the normalized Duns partitioning coefficient. So when that value approaches 0, what that indicates is that the fuzzy clustering membership matrix is a completely fuzzy clustering. Okay. All right, and then let's switch gears to this type of fuzzy clustering membership matrix. And so we can see with our eyes that this is a completely hard assignment. So every observation in the data set is assigned to one and only one cluster at 100%. And it has a 0% assignment to all other clusters. So if we were to calculate the normalized Duns partitioning coefficient for a matrix such as this, what would we end up getting? So what did you guys get for this?
I think I calculated one for this one. I didn't see the one for the 1/2 or 1 over
Oh yeah.
2 values for the other one.
Okay, yeah. So this would be a 1. Yeah. So if we end up calculating the WC first, well, what we can actually see is that we're simply, all we're doing here in this part of the equation is we're simply just adding up the squared membership value here. So basically 0 squared is simply just 0, and then 1 squared is simply just 1. So basically we're just adding up all of our M1s from this matrix here. So what we end up getting is 1 over M times simply just M. So that gives us a WC value of 1. And so when we plug in that WC value into our PC, the normalized Duns partitioning coefficient, then we get 1 minus 1 over k divided by 1 minus 1 over k. So that is just 1. All right. And so what this shows us is as we approach a normalized Duns partitioning coefficient, as we approach 1, what this indicates is that the fuzzy clustering membership matrix is a completely hard assignment. All right. Cool. All right, so any questions on that? All right, cool. So we're going to use all of these. So we're going to use the fuzzy C-means clustering algorithm as well as the normalized Duns partitioning um, coefficient to cluster our MNIST data set in a more nuanced, hopefully more nuanced way than what the k-means clustering algorithm would return to us. So, unfortunately, fuzzy C-means is not a part of scikit-learn. So you will need to, I don't know why this was blanked out, but you will need to run pip install skfuzzy to get this fuzzy C-means clustering algorithm. Okay. And so we're going to import the C-means function from this skfuzzy package. Now, unfortunately, the C-means function, it doesn't belong to scikit-learn. And unfortunately, the way that the C-means function works, it's not quite analogous to like the k-means clustering algorithm from scikit-learn. So it's some slight differences in how the function works. So we'll talk about that in this unit. Now, what you'll notice is that we actually I didn't include any CSV files, or at least not for this MNIST data set, because the MNIST data set is so well known that it's actually a data set that you can download directly from scikit-learn. It's such a popular benchmark data set. So the way to download the MNIST digits data set is just to import this object here, so the load digits function. And so if you simply want to get the MNIST dataset, you can simply just instantiate an object with the load digits function. Now this object is actually it's an object that resembles a dictionary in basically how it functions essentially. So a dictionary in Python, I'm not sure if I mentioned this yet, it's a dictionary always comes, so it's always defined by a set of curly brackets, and then the input to the contents of the dictionary are within the brackets. And then a dictionary always comes with a set of corresponding keys and values. Actually, yeah, I think I did talk about this before. So for instance, the data key corresponds to the data value, or in other words, a NumPy array of the actual pixel values for each of our digits in this data set. So we're gonna use this key in the corresponding value. And in addition, we're also going to use the target key and the corresponding value. So what this represents is the corresponding array of what digit the picture actually corresponds to. So we're not really going to use the rest of this here for our analysis. So what we're going to do is basically I'm going to take that digits dictionary. Now, technically, it's a scikit-learn utils bunch object, but it's basically a dictionary. So we're going to extract the data set first. And now technically this is in the form of a NumPy array. So we're going to put this into a data frame in just a second. But what I'd like to do is actually scale these pixel values first, not with z-score scaling. And we'll talk about why that is in just a bit. But rather, what I'm going to do is I'm simply just going to divide by the highest possible pixel value that you can achieve, such that these actual scaled pixel values are going to be between 0, i.e. black, and 1, i.e. white. Okay. Basically, if you ever want to look at the shape of a NumPy array, you can use the NP shape. And so what this shows me is that there's 1,797 images, and they each correspond to 64 pixel columns. Okay. And then I'm also going to extract the pre-assigned class labels, i.e. the digit that each image is a picture of. And so I'd like to put this data set into a data frame because that's what I usually like to work with. So this makes the task of creating the column names for this data frame a little bit laborious if you don't understand list comprehension in Python. But basically, if you ever want to quickly make a list based on some sort of for loop that you like to run to create the list, you can use this list comprehension um, setup in Python. So basically, what you do in this setup is you say, so basically, what I'd like to do is I'd like to create a list that says like pixel 0, pixel 1, pixel 2, so on and so forth. I'm going to set up my for loop that I would originally set up just normally. So I'm just going to say for I in the range of values between 0 to 63. And then I'm going to use string formatting. And I'm going to basically say, so whenever I put like a %s inside of a string, that's basically setting up like a fill in the blank in the string. And then basically what comes after the string that I've just stipulated, basically after I'm writing a %sign, that this value here is going to be plugged in to that blank. So basically what I end up getting is this list of column names, pixel 0, pixel 1, so on and so forth. So these will be my column names that I'm going to plug in here when I put that NumPy array into a pandas data frame df here. Okay, and then furthermore, I'm going to add on my actual pre-assigned class labels here. I'm going to call this the actual digit. That's what it represents. All right, cool. So I formatted my data set in the way that I want it to. Okay. And again, I'm just gonna, I simply just want to cluster the pixels. So I'm gonna, create another data frame. I'm gonna drop the actual digit column here. Now, what you're gonna see in your projects, as well as, like in any unsupervised learning analysis, like we mentioned, an unsupervised learning analysis is simply just a more sophisticated descriptive analytics technique. So as you see with like any, machine learning or data science analysis, it's always a good idea to explore your data set first, using more of the basic descriptive analytics techniques, because this can give you a sense as to, how your more sophisticated algorithms might perform. So for instance, what I would want to do is, first, well, let me just see how many digits do I have of each type in the data set. So I can use the value counts. Now, in addition, so this is our first time exploring images. So it's, we want to use slightly different, basic descriptive visualization techniques to summarize, our images in this data set. So let me just quickly grab what I'm doing here. So what I'd like to do, it's usually a good idea to look at a sample of observations or sample of images in your data set first to give you a sense as to like what are you working with? What might you need to consider when it comes to using the more sophisticated techniques? So what I'm going to do is I'm going to simply visualize the first 3 digits or first 3 images that correspond to each digit into this data set here. So I'm going to iterate through digits 0 through 9. Okay. And then I'm going to take my pixel data frame, and I'm going to filter it for just the current digit that I'm considering. So the first case, digit 0. Okay. This creates this filtered data frame here. Okay. And if you would ever like to visualize a image in Python, this is how you're going to do it. So basically this image show is what we're going to eventually end up using to visualize each of these images here. But basically, because I'm going to be creating a lot of images, I'd like to get a little bit more sophisticated, I guess you could say, in how I'm setting up my subplots. So what I'm doing here is I'm setting up a subplots figure, which is going to contain, in this case, 3 subplots. So 1 row and 3 columns of plots. So that's going to be this here. And I can also set up the figure size. And so the important thing that I'm grabbing from this subplots function is going to be the axis object, which I'm going to be updating down here eventually. And so because I'd like to, plot my first 3 0 digits in this 0 filtered data frame here, what I'm going to do next is I'm going to iterate through I equals 0 to 2. And what I'm going to do is I'm going to take my 0 filtered data frame, and I'm going to use the iloc function to locate the observation that corresponds to the 0th, or basically the first row in this data frame, then for the second row, or then the third row, so on and so forth. And then, so basically I'm going to take this 64 dimensional array that corresponds to the first row in this data frame here. And what I'm going to do, I'm going to put that into a NumPy array. And the more important thing that I'm going to do is I'm going to take that 1 by 64 array, and I'm going to reshape it into a 8 by 8 matrix. Or in other words, I'm going to put it back into my 8 by 8 pixelated grid format, if you will. And then I'm going to unscale those pixel values by multiplying by 255. So what this gives me is my image that I'm going to plot. Okay. And then, so I'm going to use that image show function to actually plot that image. But the way that I go about updating a given subplot in a subplot figure is basically I take that axis object that I created above when I first instantiated the subplots. And in this case, I'm going to tell it, okay, I'm going to use the image show on this particular subplot here for axis object 0. And then, once I move on to I equals 1, I'm going to update that particular subplot corresponding to axis or subplot 1, so on and so forth. And a couple of other things I would want to do just to visualize this image a little bit better is basically get rid of like any tick marks and get rid of any grids, that kind of thing. And so basically what I've done here after I've finished with this sub for loop or inner for loop is I've basically updated my 3 images in this subplot. And so now that I'm done updating those 3 images or 3 subplots, I'm ready to actually show the overall figure or the overall subplot figure with all these 3 plots here. Okay, so on and so forth. I'm going to do the same thing for the remaining 9 digits in the data set. So what this gives me is a sample of what my 0s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s and 9s look like. Okay. And this can, even simply just by looking at the images, we can get a sense as to, what kind of problems perhaps our supervised and unsupervised learning analyses might run into. So for instance, we can see that, some people when they write a 9, they actually, they actually put the hole there. But then this is a very sloppy 9, right? Like they don't have a hole. I'd personally have a hard time figuring out what this is meant to be. And then same thing for this, like people write 8s, kind of sloppy, but what we can see with the 0s though, these are, at least from the ones that we're looking at, these are relatively unambiguous. So simply just by looking at your images, that can give you a sense as to what you might want to be careful of, if you will, when using more sophisticated algorithms. And in addition, you might also want to get a sense as to like how much variability you might expect to see in the images for each of your 10 digits. So one way that you can go about exploring that is by visualizing the mean of all the images for each digit in the data set. So how you can go about doing that is you can take your data frame, which has each of your 64 pixel values and your actual digit column as well. And you can use the group by function, and they have this in R as well, so it's basically works the exact same way. I'm going to group by my actual digit value first. And so basically for each of my 0 digits, I'm going to calculate the mean pixel 0 value, the mean pixel 1 value, so on and so forth. Okay, so that creates this digit averages data frame here. And to get a sense as to how much variability I might expect to see in each of these 10 digits, I can plot that average digit image that I've just calculated up here. So I'm using a similar subplot function that I just described above. So what I'm going to do now is I'm going to iterate through each of my digits from 0 to 9. And then rather than using the iloc function, I'm going to use the loc function, which works in a slightly different way in some scenarios. So the loc function, what that does is it looks up the corresponding index value in the given data frame that we're referencing. So basically, if I wrote, so like for instance, if this index here was, if it wasn't 9, if it was something like digit 9, then if I put digit 9 here, this is the row that it would look up essentially. But yeah, so basically if I put a 9 here, it's going to look up this corresponding row from that data frame. Okay, I'm going to do the same thing again. I did set up a subplot figure, this time with 10 images, so 1 row and 10 columns of subplots. And then I'll stop after this to actually update each of the corresponding subplots here. Oops. I'm simply just going to use that image show again. Okay, after reshaping each of the flattened arrays in this matrix here. So very quickly, so what I can see here is that 0, it looks like a pretty crisp image, right? So we don't see like a lot of grayness like we do see in some of these other images here. So that what that could be an indication of is that, for instance, there's not a lot of variability in how people draw the 0. On the other hand, if we take a look at like the 8 or the 1, for instance, these images look a lot less crisp. We see, a lot more gray showing up on the edges here. So that could be an indication to us that people write 1s and 8s in a wide variety of different ways, such that we're not seeing as much strong agreement in what all those images look like. Okay, so I guess we'll have to wait for the actual cluster analysis until after spring break. So I know you all are waiting on bated breath for that. But yeah, so that's what we'll do. I guess not next Tuesday, but the Tuesday after that. Okay, cool. Yeah, so I know I went over, but yeah, I'll stop recording. And yeah, hopefully everybody has a nice